waste my time making stuff and not giving it to you.
What? No problem.
All right, so we are going to review some material for the exam. This exam is covering a lot of stuff, and my review is only covering the first, 2/3 of it. The last third, hopefully, is still fresh in your mind. Cool. First, I was asked at the end of class on Friday about the special question. And the special question is one that is asking you to show your reasoning ability, your ability to look at data and make scientific conclusions from it. So I'm going to give you some data that is correct data, probably related to astronomy, but definitely not something that we've already studied. Right? So it's not something where you're going to be like, oh yes, I remember this, it was this. And you are going to be tasked with looking at that data and seeing, what does this tell me? What scientific conclusions can I draw from this data? So it's looking for scientific reasoning. Also, I thought it was very cool. After class on Friday, I went home, I was reading my news feed, which you might guess is a little science heavy, and I saw an article on popsci.com about gravitational waves, because we just talked about it. And it was about this guy who was hoping that sometime within the next 50 years, they might have detected enough gravitational waves to understand the Hubble constant, which we haven't learned about yet. And, well, to get a third measurement of the Hubble constant, I should say. And then as he was flying home from a meeting where he presented on this, they made another discovery of gravitational waves, and got home all excited. Hey, maybe now we can, he's being optimistic, he thinks maybe within 5 to 10 years we'll have that data. That's really optimistic, but I thought it was a pretty interesting read. So you might, go read that when you're tired of studying for the exam. Chapter 13 was covering asteroids and comets. I put there in the order that is listed in the chapter title, but in the sequential order in the chapter, it starts with asteroids. So asteroids, first discovered actually back in the 1800s. I know I did not talk about when the first asteroid was discovered. That date won't be on the test, but just for reference here. Most of the asteroids are in the asteroid belt that's between Mars and Jupiter. Not all of them, but over 75% of all known asteroids are there. Remember, we talked about the asteroid belt is actually not very dense. If you watch Star Wars, you got to zig and zag and move all about to get through the asteroid fields. But in fact, the asteroids are on the order of 1 kilometer or 2 in diameter, and the space between them is on the order of 1,000,000 kilometers or so. So it's not a difficult job to pass between them. Most of them are very dark, like lumps of coal. They only reflect 3 to 4% of the light that hits them. There are a few, like I think it was Vesta. Remember, I screwed that up when we were talking about it before. That are actually very reflective, like 30%. That's kind of special. The 3 major types are C, S, and M. C for carbonaceous, things that are, they have carbon-based compounds. S for stony, silicate-based, and M for the obvious metallic-based. And they have moons, just like other things do. So Ida and Dactyl is an example of a system where Ida is an asteroid with a moon Dactyl orbiting it. How is it possible for asteroids to have moons? What makes object A orbit object B? Gravity. And they're still going to have gravity. It's much smaller, but they just have to go slower than to maintain the orbit. Comets. Comets are actually named because they look kind of like comets. The first repeating comet was discovered by Edmund Halley. Halley rhymes with Valley. Halley, who was actually a friend of Newton's and used Newton's laws and ideas to analyze, and came up with about a 76-year period for it to return. Last time it came around was in 1986. So 1986 plus 66 means what? If you do the math, I think that means that it'll come around 2052 or something like that. I'll be an old codger at the very least when it comes around again, because it came around when I was in college. Comets are, well, the prevailing theory now is dirty snowballs. You have a nucleus that is made up of primarily ices and dirty stuff, things like silicates and the carbonaceous stuff. So it's a mixture of ice. Now, when we say ice, we don't mean necessarily water ice. There's a lot of water ice. We also have other types of ices, methane, ammonia. And so when they're far away from the sun, they're just hanging out. They're the same exact type of stuff as Pluto, we think. And they hang out where Pluto hangs out. In fact, Pluto is the same type of thing. It's just that Pluto has a reasonably circular orbit. Now, compared to the Earth's orbit, Pluto is a little eccentric. But if something were to make Pluto fly way off path so that it became very eccentric and came close to the sun, then it would be a comet. It'd be an enormous comet, because right now it's, I think, the second biggest cometary type object we know of. But it's that kind of thing. When they get close to the sun, then the sun starts affecting it. It starts melting the ice. And, well, melting, it's sublimed. It goes directly from ice into gas. And that gas is broken up into two categories: dust and ionized gas. The dust tail is going to trail behind the comet. It's going to be affected by the solar wind, the radiation. There's actually solar radiation that affects, as well as the charged particles, mostly protons and electrons, flying away from the sun. So it's going to not just trail behind the comet, it's going to also be pushed away from the sun. The ionized tail is strongly interacting with the solar wind, and so it points directly away from the sun. So when you watch a comet, you'll have one tail that's always pointing away from the sun, which leads people to get very confused when it's going away, when the comet itself is moving away from the sun, so it's chasing its tail. Right? It's going in the direction of the tail, roughly. Remember that word eccentric means not very circular. Comets come from two different locations. We have the, quote, short period comets, and in the textbook it lists a number of comets with periods under 10 years. Those are things that are essentially coming from the region where Pluto is, but something has made them, instead of doing nice circular orbits, go diving in. What would that something be? It could have been a chance encounter with a more massive companion out there, or it could have been some star came close enough to our solar system to cause them to deviate. It doesn't have to come really, really close to make an effect to make them deviate. So comets can be produced over time. That's an important thing to keep in mind, because as creationists, we have some people who say there can't be comets if the Earth is, billions or billions of years old, because they make the assumption that no new comets can exist. They have to have always been in that cometary orbit. And scientists know a comet, since the sun is making it sublime every time it comes close to the sun, it only has a finite number of orbits before it's done. Oh, yeah, I forgot. I mentioned the Kuiper. Well, I started to mention the Kuiper Belt. The Kuiper Belt is the region that is in the same plane as the planet's orbit, just farther out. And that's where the short period comets come from. How do we know that? How did Kuiper come up with this idea? Because he noted that most of the short period comets all come in the same plane. And using Kepler's laws, you can calculate how far out they're going to be based on the period that they come around. Remember Kepler's second law, third law. Period squared is proportional to semi-major axis cubed. So if you measure the period, you can calculate the semi-major axis. And since it's coming close to the sun on one side, you just say its distance away is twice the semi-major axis for where it's coming from. Then you had the Oort cloud that Oort predicted based on the long period comets. The long period comets, because it's a long period in that relationship with with Kepler's law, we know that the long period comets must be coming from much farther away. And those were coming in at all different angles, not just coming in the plane. And so Oort predicted that there should be a cloud out there that's a spherical cloud about the solar system. That is where they come from. Then talking about meteors. Meteors are bright flashes in the sky. Meteors are produced when you have something traveling through the atmosphere and it gets ionized because of the collisions. And this ionized thing then is going to excite electrons and atoms it passes near. And those atoms that it passes near the excited electrons fall back down to lower energy states and give off light. So it's not actually coming from the object going through the atmosphere. It's coming from the atmosphere because of the object going through it. So that's the meteor. It's light. A meteorite is an object that strikes the earth. Now we had that funny thing about almost all meteors are little things like the size of a grain of sand. And all meteorites start out as some kind of rock. So how can it be that all meteorites start out as some kind of big rock and almost all meteors are produced by a little piece of grain of sand? How do those two work out?
Well, the meteorite would have to be big enough to be able to make it through the atmosphere.
Right. To make it through the atmosphere to the Earth, it's got to be big enough to survive. And so almost all of them are tiny, but they don't survive. Now, if you were on the moon, you don't see meteors in the moon. Why don't you see meteors on the moon? If you're on the moon, you look up in the sky, oh, there's no meteor showers. Why not? No atmosphere. The light's coming from the atmosphere. There's no atmosphere. Instead, what happens?
It just strikes.
Yeah, it just strikes the surface. So then you do have, if you will, the meteorites are these little things. And if you were on the surface of the moon during a meteor shower, you would be getting pelted by these little, I say pelted. Chances of getting hit are probably pretty small. But if you were big enough in size, you would be getting pelted by all of these little grains. Meteor showers occur, when the Earth passes through a cloud of dust and debris left over from a previous comet. Tomorrow marks 185 years since the Great Meteor Shower of 1833. On Facebook this morning, I saw somebody posting an article about this, and it said 180th anniversary. And so I blindly, tomorrow's the 180th anniversary. Wait a minute. Went back and looked at the article, which was actually published a year ago today. But of course, that's not the right date. It was copied from a previous, you know how clickbait works. But it is 185 years from tomorrow when the Great Meteor Shower of 1833 occurred, which in Seventh-day Adventist lore is very important because that's the date, November 13, 1833, that we traditionally say the sign at the end, the stars fell. Meteorites, just like asteroids, come in the carbonaceous, the stony, and the metallic. You have similar differentiations for meteorites. You have, there's three classes here plus one more. I first put four, but the textbook is very clear. There's three, but it talks about the fourth. There's primitive, which is meteorites that appear to have, been from old material, not something that's gone through heating and so on. Then there's younger ones, differentiated stones. What does it mean to be differentiated? Basically means that it's been separated in some fashion. Differentiation is part of the planet building process. When you have something that is a hot, molten young planet, the more dense material sinks to the center, the less dense material flows to the surface. So differentiated stones are ones where you've had that occur, where you've had the stone separating from the metal. irons and stony irons. The textbook is very clear. Irons and stony irons are very unlikely to have come from the earth. Because in the earth, we generally don't find just iron rock. We find rock with lots of little iron in it, but not iron rock. So if you find an iron rock, meteorite's probably not going to be from the earth. And stony irons likewise because of the iron rock in them. So where does our solar system come from? The solar nebula theory is science's answer. Solar nebula theory, we have a big cloud of gas. And we understand this now in context of chapters 20 through 24 as well. Big cloud of gas, shock wave comes and hits that cloud of gas. What kind of cloud of gas would it have to be? This is moving into chapter 21-ish area. What kind of gas or cloud is that going to be? To make a star. It is largely hydrogen. After all, the universe is essentially hydrogen, over 70% of all atoms. But we had different types of nebulae, and it was those cold molecular clouds. Those are the ones that are likely to be the nurseries for new stars. Now, we talked about it first here, just talking about our solar system. But now we understand from the more recent chapters that our sun almost certainly did not form as a single star. It would have formed as a single star system with lots of other star systems around it formed at the same time, because you probably had a really big cloud and only a small amount of that, percentage-wise, became our solar system. If that's the case, though, where are the other stars that we formed with? There are a number of conclusions you can draw. There's not one correct answer. Probably the easiest conclusion is that we were part of a poor nebula. Didn't produce that many stars, maybe a couple thousand. A couple thousand, that makes an open cluster or an association. And those don't last very long because you just don't have enough mass to keep them together. So that's one good option for what happened to our companions. There's other options. One option is when we learn about galaxies, which is what's going to come up after the test, we will learn that we are currently interacting with another galaxy, and the tail of that galaxy, when we say the tail, we mean stars from the other galaxy, is currently crossing through the plane of our galaxy where we are. So some of the stars in our vicinity, and of course our vicinity now is a very large vicinity, are not from the Milky Way galaxy. They're from another galaxy that is currently battling and losing badly to the Milky Way galaxy. And so, some people say, well, we could have been from a different galaxy. For the second time today, I will quote John Pinette. I say nay, nay, because the direction of our orbit is not consistent with being part of the other galaxy. It's consistent with being part of the Milky Way galaxy. A little disappointing, actually. It would be cool to be like, yeah, we came, we lost. Okay, the terrestrial planets formed inside of the frost line. That frost line is an important concept. To understand we have two different types of planets, you observe that and then you're like, why? That's the whole scientific thing, why? And the answer that scientists come up with is that planets formed by, first you have condensation. You have things cool and then molecules stick together. We see that all the time. You go out in the morning and you have dew condensing on the windshield of your car. That's the first step. But if you're inside the frost line, the temperatures during planet formation were high enough that stuff couldn't stick together, except for very high melting temperature stuff like iron and silicon dioxide, things like that. And so that's what primarily the inner planets, the terrestrial planets, are made of. The only kind of stuff that could condense at that high temperature. Now, after you have stuff condensed together, you form little grains and planetesimals, and then you have accretion. Accretion is just two things come and hit each other and it's like two pieces of mud. They just come and stick together. It's the condensation is molecule by molecule process. Accretion is chunk by chunk. And so you have chunk by chunk accretion then of these little planetesimals to form protoplanets and eventually planets. So that's how the planets got here, we believe. The ones beyond the frost line, they could have condensation of things like hydrogen or methane or water. And so they have a lot of stuff that they could grab onto. Hence, they grew a lot quicker and much bigger. And they have lots of atmosphere because of that. Exoplanets gives us a place to test the ideas of the solar nebula theory. Right? As people come up with this idea about how our solar system formed, then they say, well, you should have this kind of thing and not that kind of thing. And then looking for exoplanets, planets that are found for other stars, orbiting other stars, they can look and see, do we have the kinds of things that our theory predicts should occur? And the answer is generally yes. I put here the stages of planet formation again. Accretion, that's stuff sticking together. Differentiation, we just talked about, heating and separation by density. Cratering, that's impacts. In the early days of the solar system, you would have had lots of debris flying around because you have lots of stuff that's sticking together forming little chunks. A little chunk hits a bigger chunk, it puts crater in it and stays. Flooding would be originally volcanic flooding, magma flooding the surface. Later on, from other things like impacts with comets, potentially water flooding, and then the slow surface evolution that is still going on today on Earth because we have lots of atmosphere and liquid water. And the Earth's first atmosphere was probably things like carbon dioxide, methane, lots of hydrogen. Actually, hydrogen would have been the first one, then the second one would have been the carbon dioxide and methane stuff that gets baked out of rock. And then the third atmosphere probably came from comets containing nitrogen, 79%, oxygen, 21%, and the water that we see on the surface of the Earth. All right, so we're through 2 chapters. Yeah, that's why I didn't do the final 3 or so in my review. The sun. By analysis of the absorption spectra in the sun, and from taking the knowledge we have and looking elsewhere in the solar system and universe, as well as the theories on nucleosynthesis, the creation of elements, we come to the sun being 92% hydrogen and 73% by mass, 92% by atomic number, because the mass of a hydrogen atom is like 1/4 the mass of a helium atom. So you get different percentages depending if you're talking about number of atoms versus the amount of mass. But it's still predominantly hydrogen for the sun. That's good, because what is the fuel in the sun? Hydrogen. Okay? The photosphere is what we see. The photosphere, about 5,800 kelvins, is the region where the atmosphere gets thin enough for light to get out of the sun. And so that's where we see the surface of the sun. It's not a solid surface. It's an ionized gas, what we call a plasma, where everything is ionized. There's no electrons bound to any nuclei in the sun. The sunspots that we see on the surface of the sun are magnetic storms. The temperature has been depressed by the strong magnetic fields. The strong magnetic fields stop the convection flow, and thus the temperature gets cooled because you can't bring up heat through convection. And so you might have temperature of 4,000 kelvins in a sunspot. How do we know they're magnetic? Because of that Zeeman effect. You look at spectral lines, and in a strong magnetic field, the spectral lines will split. And by measuring how much they split, how much wavelength shifts, you can determine what the magnetic field strength is at the point where that light's coming from. And so they can determine what the magnetic field strength is in these sunspots, and they know it's very strong. I've done a lab with my students sometimes, a higher class, where they have to measure that splitting of the Zeeman lines and then determine what the magnetic field is in the sunspot. As we had on the last test, granules, it was on a test, wasn't it? Or was it a quiz? It's a quiz, okay. Granules are evidence of convection at the surface. Granules, using Doppler shifts, we can see that the bright parts are coming toward us, the dimmer parts are going away from us. The bright parts are hotter because remember, luminosity is proportional to temperature to the fourth power. And so the hot material is coming toward us, the cold material is going away. That's classic convection. Hot material floats up, cold material sinks down. The chromosphere is the region above the photosphere, and that has a pink color because of Balmer emission. And then above the chromosphere, you have the corona, the crown of the sun, which is back up to million kelvins. Now, the core is around 15 million kelvins, so it's not as hot as the core. But the surface is only 5,800 kelvins. It was a big question for scientists. How in the world can the corona be so hot when the surface, the photosphere, is not so hot? And the answer came from its energy that's been transported by the magnetic fields to get it hot up there. Continuing on with chapter 15. The solar wind is the particles, like I said, mostly protons and electrons that are being constantly blown away by the sun. The corona is constantly blowing particles away. In fact, if you were to ask, where is the extent of the sun? Where does the sun end? It's a really poor question because you don't have a clear-cut answer. You could say that we're within the sun right now because we're within the solar wind. In fact, the heliopause is the place where the solar wind stops. And you might consider the sun going all the way out to the heliopause. We usually just say the corona and don't talk about the extent to where the corona is. So we have that solar wind. The sun does some interesting things. First, it cycles. On average, it's about every, 11, yeah, because it ranges from 9 to 14. 11 is somewhere in the middle between 9 and 14. 13 is near the edge of that. About every 11 years, the sun switches its magnetic orientation. So the north magnetic pole becomes the south magnetic pole, the south magnetic pole becomes the north magnetic pole, which is really bizarre. But then again, the Earth does that too. It's just a much longer and much less reproducible period. I said for the sun, it ranges from 9 to 14 years. On the Earth, it averages about once every, I think it's around 200,000 years, and it's been almost a million years since we've had a magnetic field reversal, according to the best scientific measurements. Right? No one was there at the time to record it. Make sure you understand the whole process of magnetic field lines. You have the differential rotation. That is, the equator rotates faster for the sun than it does closer to the poles. And so magnetic field lines start getting pulled around instead of having a nice uniform thing like this. And as those magnetic field lines get distorted, it causes magnetic fields to go off in random directions, making magnetic fields, strong magnetic fields come out through parts of the sun, making the sunspots. And those sunspots start like 30 degrees north and south of the solar equator, and then as they get more and more tangled up, they move closer and closer to the equator, and then, basically it's Control-Alt-Delete, it resets, flipping things over. The sun has prominences. Prominences are those cool things where you have, here's the surface and you have magma going, or not magma, you have plasma going in a nice loop like that. That's a prominence. Why is it a nice loop like that? Because it's following the magnetic field lines on that are coming out of the sunspots. And so you're going to have sunspots coming in pairs, one where the magnetic field line is coming out, one where it's going back in. So those are prominences. Now those prominences will sometimes erupt. They will sometimes snap and shoot a lot of material outward into the corona at very high speed. And so those are called solar flares when that happens. And sometimes you will have the corona responds with its own eruption, which is called the coronal mass ejection. And when those things, the flares, the coronal mass ejections, are aimed at the Earth, right? They can be going in any direction from the sun. When they hit the Earth, it can be devastating for us. There was a whole section in the textbook on the devastation potential of that stuff. Now, we usually don't think of them as devastating. We think of them as pretty. Because when those things hit the Earth, they cause excitation of gases in the upper atmosphere, giving us northern lights and southern lights. And it's mostly northern and southern because the Earth's magnetic field protects us that the solar wind is deviated away from us here and goes closer to the poles because of the Earth's magnetic field. How does this? I don't know if this is new chapter or not. The sun produces its energy through fusion of hydrogen into helium. Remember, we have the proton-proton chain, which is two protons produce a deuterium, and then a proton and deuterium, I think it was, create a hydrogen or a helium-3, and then two helium-3 create a helium-4 and two protons. I think that was the process, something like that. It's a complicated process that has as a net result 4 hydrogens produce 1 helium-4 plus some neutrinos. Those neutrinos were an important part of the process. Those neutrinos were predicted, and then people observed neutrinos, and what they found was only about 1/3 as many neutrinos as predicted. And we've been talking a lot in this class on the final exam. It's going to come back again, same question for the first exam, about the scientific method. The scientific method, step 3 of what we learned was to run a test of a prediction. And so here's a test of a prediction. There's a prediction of how many solar neutrinos we should be receiving, and they were only getting like 1/3 as many as predicted. And so what do you do if your test fails? Or your hypothesis fails the test, to be more exact. What do you do then? You go back and you modify your hypothesis. So that's where scientists were. Where were we wrong? And it turned out they weren't wrong. They misunderstood neutrinos. Neutrinos come in 3 different flavors, and they can change between those flavors. And so it turns out all of a sudden, whoa, by the time they get here, everything that was initially the electron neutrino is now going to be equally mixed between the 3 flavors. And the electron would be now called the light one if you look up above Levi's head. Where you see the neutrinos, it says the light neutrino and the medium neutrino and the heavy neutrino. It used to say the electron neutrino, the mu neutrino, and the tau neutrino back when I was a kid. A kid like your age. You need high temperatures for fusion to occur. Why do you need high temperatures? You need high temperatures because you have to have particles moving fast enough. Remember, temperature is a measurement telling you how fast the particles are moving. You have to be moving fast enough to overcome the repulsion between charged particles. 2 protons naturally repel each other. And so you have to go really fast to have enough energy to actually get together. You also need high pressure because the chances of 2 things colliding increases dramatically as you increase the pressure. And so high pressure necessary to make it likely that you're going to have 2 things collide to make fusion. Fusion can occur because when you put 2 protons together in a nucleus, it's lower energy than if they're separate. And according to Einstein's relativity, it actually will release energy in accordance with a decrease in mass. So we have this equation up there at the top, E equals mc squared, nicely split between 2 lines to obfuscate it. The energy released by the sun is being transformed from mass into thermal energy via that equation. So the sun is losing mass for all of the light that it sends to us because it's converting energy from mass form into the light we see. Moving on. If the sun's core was a little hotter, what's the temperature in the core of the sun again? approximately 15 million kelvins. If it was a little hotter, like, 16, 17 million kelvins, it could shift into the CNO cycle, which is the cycle where a carbon absorbs a proton, becomes, if you look right there, you can just see, after carbon becomes nitrogen, it actually becomes nitrogen. It's a radioactive nitrogen, it decays, it becomes carbon again. Absorbs another one, becomes stable nitrogen, goes through the same process, becoming oxygen, decays, comes back to becoming oxygen, and then absorbs another one and breaks off a helium and goes back to carbon. So the CNO cycle is a little more efficient at converting energy, but it requires a higher temperature than the sun has to make it likely to occur. At all points in the sun, you have equilibrium between the outward push from the explosion in the core and the inward pull from gravity. And that equilibrium is called hydrostatic equilibrium. That's necessary for it to be a stable star. In the early stages of the star, as well as the death stages of the star, they can go through some oscillations where they're unstable. And so you got more pushing out than pulling in, and it starts expanding, and then it reverses. You might remember this line because it was the title of one of the two songs. The sun is a miasma of incandescent plasma. Don't worry about the miasma word. What does incandescent mean?
It has something to do with white lights and light bulbs, that's all.
Okay, it has something to do with the light bulbs. Incandescence is giving off light because it's hot. And so traditional light bulbs are incandescent light bulbs. We run electricity through them and make them hot, and then they give off light. These here are not incandescent lights. These are fluorescent bulbs running by the same mechanism that gives us the Balmer series, the Balmer light from hydrogen. That's what is going on in these. Actually, it's a little more complicated because it's basically mercury in there, which gives off ultraviolet light, and then there's powders that absorb the ultraviolet light and give off visible light in different colors from these. So it's a little more complicated than just the light given off by the plasma, because inside of those tubes you have a plasma. So incandescent gives off light because it's hot. Plasma, ionized gas that has electrons removed. The interior of the sun, the very center of our sun, is a radiation zone. Radiation means that you have electromagnetic waves that are carrying the energy out. But those electromagnetic waves are constantly being absorbed and re-emitted in random directions. So the transportation of energy through that center part is very slow. But then you get to the outer portion. We've already talked about that. What mechanism for heating do we have in the outer portion of the sun? Uh-oh. As evidenced by granules. Convection. So out here we have convection currents. And that's much faster because it's directed. The heat goes one direction instead of changing directions all the time. And so it goes pretty quick through there. So it might take 100,000 to 1,000,000 years for energy to go from the core of the sun, where it's being produced from the fusion, to the photosphere where it leaves and comes to us, with the vast majority being while it's in the radiative zone. How we know anything about the interior of the sun is pretty amazing, and it comes from helioseismology, from actually studying the shaking of the sun that's caused by things like when you have a flare or a coronal mass ejection. The flare or the coronal mass ejection sends a rebound wave into the sun, and then that causes the sun to wiggle and jiggle. And so they examine that wiggling and jiggling, just like on Earth, we examine the wiggling and jiggling of the Earth when we have an earthquake to determine what's going on inside. All right. 10 minutes, and we're finally getting into stuff where I think I can go quicker. That was some pretty dense material about the sun. Analyzing the starlight. Luminosity is a measurement that tells you how much light is coming from an object. So it's proportional to the temperature to the fourth power and the area, which for a star is the radius squared. So the luminosity of a star is proportional radius squared times temperature to the fourth power. Brightness is how much light we receive from it, which has to do with its luminosity and its distance. So using brightness comparisons, you might be able to find something about the luminosity or the distance. If you know the distance, you find the luminosity. If you know the luminosity, you can find the distance. So there are some very important equations to go with this. Now we have the magnitude scale that Hipparchus came up with about 150 BC. You can imagine when Jesus was a child, this was roughly 150 years after this magnitude scale was first devised. If he had been going to the highest level schools of the land, he might have been taught these things. Now, he learned at his mother's knee, which suggests that he was taught the knowledge everybody knows, not the highest level knowledge. But it was something that he, could have been taught about. He also could have been taught what the radius of the earth was, because that was well known at the time he was alive. Nowadays, we have that magnitude scale that's formalized. Back in Hipparchus' day, magnitude 1 was really bright. Magnitude 6 was really dim. He took like 1,000 stars and broke them up into these magnitudes. And then people noticed that, well, if we measure the brightness, the amount of light we receive, that a difference in the magnitude of 5, is equivalent to brightness 2 is equal to 100 times brightness 1. So the delta M is the magnitude, first, second, third, fourth, fifth, sixth, and then the brightness is how much light we receive. And so from that, those two numbers, scientists came up with a calibration that says that 100 to the 2/5 raised to the... I did that backward, darn it. I did it backward. Basically that equation. Now I didn't memorize this equation. It's like magnitude 2 minus magnitude 1 is equal to 2.52 natural log of brightness 2 or brightness 1 over brightness 2. I think that's what it is. I didn't memorize it. You don't have to either. You will have it on the equation sheet. You'll have this equation in case I wrote it wrong. You'll have it on the equation sheet too. But you do need to be able to use these things. If you have this star is a 2.5, and this one's a 1.0, what's the ratio in their brightnesses? You need to be able to put the numbers into the equation. You get that ratio. And I said that this is the hardest math that you guys have in the class. It's not the hardest thing in the world, but it's not the easiest thing in the world. So make sure you review that and can do the math with those. Also, we have the absolute visual magnitude compared to the apparent visual magnitude. Absolute visual magnitude is based on how bright it would be if you were 10 parsecs away, a standard distance away. In other words, absolute visual magnitude is actually giving you luminosity information. So if you know the absolute visual magnitude and you know the apparent visual magnitude, you're going to be able to calculate the distance. So make sure you look at those equations so you can do that calculation. You can determine the distance by knowing what the difference in the absolute and the apparent visual magnitudes are. Colors are an important thing. Remember, hot, blue, cool, red. That's the colors from incandescence. Not what we have on a sink faucet, but it's still the way it is. So when you see a blue star in Betelgeuse, you say, woo, Betelgeuse, excuse me. in Orion, the blue star is Rigel that I was referring to. You see a blue star, you say, ooh, that's a hot star. You see a reddish star, you say, ooh, that's a coolish star for a star. Know the spectral classes and rough temperature ranges. Who knows the spectral classes? Okay. People are slowly. What was our mnemonic?
If it's written out, I can do it.
If it's written out, I can totally read it. Yeah. For the young ladies, I'll say the female version. Oh, be a fine guy, kiss me like this. Yo. Right, I would say the male version because it feels more natural. I shouldn't say male female because I've offended people in the past with that. With my cisgender normative. I don't know.
Oh, gosh.
Yeah, I get confused, but I hope I didn't offend anyone. I'm sorry for that. So here's a picture. You should know the order, OBAFGKMLTY. And you should have a rough idea of the temperatures. You don't have to be exact. There were a couple people on the quiz who had it all exact. That's pretty good. I was impressed. You don't have to be exact. You should know the O's are bigger than 30. The A's are around 10,000. What does it say? 7,500, 10,000? F's are like 7,500, 6,000. Okay, so you could just say 7,000, right? You don't have to know the whole range. And then G's, you know that a G2 is 5,800, apparently, because the sun is a G2. You better know the sun's a G2. And so G's are 6,000 to what? 5,000? 5,200, right? I don't know them exactly either. And then the K's down to 3,700, M's down to 2,400. You don't need to know temperatures below that for sure. But make sure you have that idea down. Also, make sure you understand the usefulness. One of your homework questions you had previously, you had how do we use spectral lines to get information about stars? And we had a bunch of different things that we get for them. So make sure you understand how that spectra is so important. We learned about telescopes earlier because our observation of stars comes from looking at light. That's it, beginning, end. And so we've got to be able to analyze that light and look at the spectral lines, give us an enormous amount of information. Got 3 minutes. Stars are predominantly M spectral class. Where is M spectral class in terms of temperature? ODA, find out, kiss me.
Lower end of
They're the coldest of actual stars, right? Because like this those were brown giants. Brown giants, you need to know the differentiation. A planet doesn't have fusion. A brown giant has like deuterium fusion, but not straight hydrogen fusion. And then an M has straight hydrogen fusion. Yeah.
Giant
Brown dwarf.
Okay.
Yes, brown dwarf. Dwarf. Okay, so these are the smallest of the actual stars, are the most common. Why? This is actually the question that I put for the analysis on the previous test where we hadn't had this yet. Why would it be that you have M-type stars are by far the vast majority of known stars? Right, this won't be your question, but it was a question that I put on a previous test for the special one. What ideas can you come up with?
You're not going to need as much mass, so it's easier for the sources are smaller. Or the mass is in the larger ones.
Okay, because these M types, they're cool because they don't have much mass. That means they don't need as much mass. You could form a lot more of them. There's one option. which makes sense to me. Another one is M-size stars. The universe isn't old enough for any of them to have ever died. So everyone that's ever been created still exists. So it's going to be easier to find them theoretically simply because there should be, they're longer lived. Over time, they're going to be dominating. If all stars stop producing, you wait, a billion years, and you're going to have a lot more M's than anything large. Then there's other theories you can come up with, but the idea is, or theories, other ideas. The goal is for you to be able to analyze that. I think it's about half of all stars are part of a binary system, and so the binaries are very common. We have visual binaries, ones we can see that there's two stars. We have spectroscopic binaries where when we look with a telescope, when we look with a spectrometer, we can tell that there's two stars because the Doppler shift's moving about. Eclipsing binaries is a special category when one is passing in front of the other. When one passes in front of the other, then you know exactly what the orientation is. And that allows you to get the best detailed information because you don't have to make any approximations then. You know its orientation. And so, using Kepler's third law, we can determine the mass of a binary system by looking at its period. The HR diagram and luminosity classes. I'm going to end with this, mostly because it's time for me to end. Yeah. The Hertzsprung-Russell diagram, you need to be able to understand this. Know that you have the luminosity on the vertical axis with very high luminosity, very low luminosity. Notice both of these put absolute magnitude. Absolute magnitude is how bright it would be from 10 parsecs away, so it is the luminosity. The sun would be there. Then you have the temperature with hot to the left, cool to the right. Main sequence, where stars live 90% of their lives. Almost all stars you find are going to be main sequence stars because that's where most stars are. Giants up in the top right, those are stars that are in the process of dying generally. White dwarfs down here, already dead. Here you see the luminosity classes. Remember, we have that on a quiz. Make sure you understand what each luminosity class is and roughly where you're going to find it on the HR diagram. Some people, once again, nailed it on the quiz. Some people not so much. I think, a little understanding on the positioning. After all, on this one here, it doesn't even show, right? It just says giants, supergiants. Okay. Have yourselves a great day. I'll see you tomorrow for lab.
Are we just doing what we usually do for our lab, like what we're reviewing?
If it's clear, yes.
Okay.
So, please. Not because I don't want to go to the lab, but because I want to test it.
I only had one more slide. That was pretty good timing.